In this video, I introduce you to the determinant that we can calculate for matrices. Our objectives for this learning activity are to find the determinant of a 2x2 matrix, to find the minors and cofactors of a matrix, and then we're going to see how to use expansion by cofactors to find the determinant of a matrix. Every square matrix can be associated with a scalar that's called its determinant. Historically, determinants were recognized as a pattern of n by n systems of linear equations. So if we look at the system here with two variables, x1 and x2, and two equations, and four coefficients, a11, a12, a21, and a22, that solution, we can calculate x1 using this formula and x2 using that formula. So using this solution is how we arrive at the determinant. You can see these calculations are based on what we might get if we multiply along diagonals, which you'll see for the 2x2 matrix is how we calculate the determinant. So the determinant of a 1x1 matrix, so that would just be one element in the matrix, is known as a determinant of A, or we use these signs that look like the absolute value, but are actually the determinant symbols. And so the determinant is just that element if you've got a 1x1 matrix. And remember these symbols here, the two lines, now that we're in linear algebra, we think of those as meaning determinant, not absolute value. So the determinant of a 2x2 matrix, you actually saw when you were finding the inverse of a 2x2 matrix. It is also written determinant A, or using the lines on either side. And then we find that by multiplying the diagonal from A11 to A22 and subtracting from that the diagonal A12 times A21. And so our diagram down here shows a convenient method for remembering the formula for the determinant. You think about the diagonal that I've done in blue here as the first product, and you subtract from that the diagonal on the other side that I've done as the green product here. Let's take a look at Sympy to see how we do determinants in Sympy. So I'm going to bring up matrix M, which is just a 2x2 matrix with entries 1, 2, 3, and 4. And then there's two ways in Sympy that we can find the determinant of M. You can type m dot determinant, so that brings up the determinant function. Keep the parentheses empty. You can also do determinant function det and in parentheses m. And so those two ways will tell you the determinant. And we could double check this. We know 1 times 4 is 4 on the first diagonal, and we subtract from that 6, which comes from 3 times 2 on the other diagonal. And so 4 subtract 6 gives us this -2 result. So geometrically, we can think about the signed area of a parallelogram with vertices at 0, 0 down here. And then these other points, x1, y1, x2, y2. And then this last entry is x1 plus x2, comma, y1 plus y2. So we can think about the area in here as the determinant. The area is positive if this angle from x1, y1 to x2, y2 is counterclockwise, meaning we go in this direction. If you go in the other direction, you get a negative area calculation. You can visualize the determinant that way. And here's our proof. So the area A of the parallelogram is the area of the large rectangle minus the area of the 4 triangles minus the area of the 2 small rectangles. Let me draw that out a little bit more clear. So here's our large rectangle, and then we've got these smaller triangles, 4 smaller triangles, and then we've got 2 smaller rectangles in here. So we know the area of the large rectangle is going to be the length of the longer side, the x1 plus x2, multiplied by the longer height, the y1 plus y2. And then we subtract out each of these four triangles. So half x1, y1, half x1, y1 again by symmetry, half x2, y2, and half x2, y2 again. You can see the symmetry in our diagram and the triangles. These symmetric triangles are the same area, and then similarly, these triangles are the same area. So that's why we subtracted some of those products twice. And then the two small rectangles are also symmetric. Those are x2 by y1. And so we subtracted that twice. And then we can simplify this to be distribute through, right? Use your FOIL skills. You've got x1, y1 plus x1, y2 plus x2, y1 plus x2, y2. And then you're subtracting out by combining our areas of the four triangles minus x1, y1 minus x2, y2, and then minus 2 x2, y1. And so you end up here with x1, y2, which is just what we get on the first diagonal, minus x2, y1 in the second part, which is just what we get on the second diagonal. And that's the determinant of the parallelogram. To define the determinant of a square matrix A of order, also known as dimensions, higher than 2, we define what we call minors and cofactors. So the minor, we're going to call that Mij, not to be confused with matrix. So the minor has the I and J associated with it, whereas we just call matrix M. So the I and the J correspond to the row and the column for our minor. So the minor Mij of the entry Aij is the determinant of the matrix obtained by deleting row I and column J of A. So the cofactor Cij of the entry Aij is, Cij is -1 to the I plus j, so our signs are going to alternate, multiplied by the minor. So notice that -1 to the I plus j is going to be a checkerboard pattern. So if you are in row 1, column 1, that's going to be positive because it's -1 to the 2, 1 plus 1 up for I plus j. But if you shift down to row 2, column 1, 2 plus 1 is 3, so -1 to the third power is going to give us negative, and so on. So let's look at this example of finding cofactors. So here's A, a 3 by 3 matrix. And notice when we typed up the entries here, we put A1, comma 1. That's very common. It's the same thing as saying A11. Different books put the commas and different don't. So that 1, 1 is first row, first column, just like if I'd written it A11. That actually, I think, came out of Mathematica Code or one of the other computer codes typing that way. All right, so we want to find cofactor 2, 1. So that means we are going to eliminate or delete row 2, column 1, because of the 2, 1 here. So you can see here, shaded, row 2 is deleted, column 1 is deleted. And so our remaining entries are A12, A13, so you can see them showing up here in our determinant, A32 and A33. So those remaining entries are what go to the determinant. And then we have to figure out, okay, well, what's -1 to the 2 plus 1? Oh, well, that's -1 to the third, so that's going to give us a -1. So that's why we have this negative out in front of our cofactor calculation. And so you can do the determinant calculation by multiplying the diagonals. That's where the A12 times A33 comes from. And then normally it would be this value minus the second value from the other diagonal, but because this whole calculation is negative, we can just reverse the signs. So we have a negative A12, A33, and then the double negatives give us a plus A13, A32, A33. All right, what would we do to find the cofactor for the entry 2, 2? So here, now we're going to delete row 2 and column 2. So the remaining entries here are going to be used to make up our determinant values, A11, A13, A through 1, A through 1. And then we have to figure out, well, what's the sign going to be? Well, negative 1 to the 2 plus 2, that's negative 1 to the 4th. So that just works out to a positive 1. So you don't have to put the plus out front. We just did that here. So you see our result here is positive. And then we go through our determinant calculations by multiplying the diagonals. So we get the A, 1, 1, A, 3, 3 from the first diagonal. And then we subtract the opposite diagonal, A, 1, 3 times A, 3, 1. So we can use this information to make a theorem about calculating determinants. So we use expansion by cofactors to calculate determinants when we get beyond 2 by 2. So we're going to let A be a square matrix of order n. So n is another way of saying the dimension, order of dimension. Then the determinant of A is given by an expansion in any row I, where you've got J being the range of the columns. So J here goes from 1 to n. And so we take A, I, J, so all of the coefficients corresponding with row I, and multiply it by all of the cofactors corresponding with row I. And so we get these results, you know, AI1, so row I, first column, multiplied by CI1, so row I, column 1's cofactor, and so on all the way up to the nth results. And then you also do it by expansion on any column J. So you would pick your column and then start at row equals 1 all the way up to row equals n, and do a similar expansion now for that given column. So when you're expanding, you don't need to find the cofactors of the 0 entries, because we know if you've got a 0 in there for your coefficient, the 0 times the cofactor just gives you a 0 here. So if Aij is 0, 0 times our cofactor is just a 0. So that can help save time, especially for triangular matrices. And then the definition of the determinant is inductive, because it uses the determinant of a matrix of order n minus 1, right, when we do our cofactors, to define the determinant of a matrix of order n. So you would prove a theorem like this using induction, and you can give it a go if you want. You can see it gets kind of quite involved, but if we assume it's true for n and then try to use these results here for n plus 1, we'll see we'll be able to do that proof. Okay, here's an example of expanding by cofactors to find a determinant. So here I've got a 4 by 4 matrix. And so you can see I'm going to take out this row here and use the fact that there's 2 zeros in here. So this is a smart move. And so then I've got the -1 here and the 3 here. And then I pull out the cofactor matrices here. And so this is row 3. So this would be the cofactor row 3, column 1. And this would be the cofactor row 3, column 4. You want to label it. And then for each of these cofactors, we can calculate, break those down next. So calculate based on taking out the row, the bottom row of cofactor 3, 1, 2, 0, 7. So we chose that so we could leave out the 0. So here's our 2 and our 7 in the expansion there. And then we get down to the 2 by 2 determinants. So you can see how a computer might do a calculation like this. And then in cofactor 3, 4, we would choose the row 3 there also because it's got some zeros. So then we just have to do the expansion on the 2. And you can see here is our determinant, a 2 by 2 determinant, and then these become things that we can calculate more simply. So this is just the kind of thing that I would like to outsource to computing, because this is the kind of thing where if we do it by hand, we're going to get a sign error. But we can see here, following out this example I've got here for us, that we should get result 36 if we don't make any sign errors. So let's head into Sympy and use the determinant function DET to verify our calculation 36 here. All right, so I'm going to call this matrix M again. So M equals matrix. And then the first row is 1, 2, 3, 0. The second row is 2, 6, 6, 1. The third row there is negative 1, 0, 0, 3. And our fourth row is 0, 2, 0, 7. And we'll verify M, make sure I haven't made any typos here. If we go back to our slides, it looks like we've got a match with our original matrix there. And so then we can do BTM. We get it 36. You could also do m dot BT and put the parentheses since it's a function. So either way, we can verify the results very quickly using Sympy. And Sympy just did a speeded up version of what I showed you here by hand. So for 2 by 2 matrices, it's pretty fast to do it by hand. For 3 by 3 matrices, you're welcome to give it a go by hand, but you can also rely on Sympy to help with those calculations because we know you can multiply and do all these expansions, and we're happy to rely on technology to assist us.